All right, physics, hello, and welcome to the beginning of what is probably going to be the longest video that I have recorded so far. I'm expecting this video to be about an hour, so just so you're aware, I'm going to be graphing the data from table 12 in this for vector addition. So I've got this set up to try to look at most of the board behind my desk. I'll probably have to erase some of this over here. If you can't read this, this is about as big as I'm going to be writing the whole time. So I will tell you that these numbers are 30, 15, 35, 260, 30, 175. This one is the letter E, and this one is the Greek letter theta. And from there, I'll explain more as we go. I'm going to pause this real quick because somebody just opened my door and did not shut it. So I will be 1 second. All right. So first off, I've got a coordinate plane here with the x-axis and the y-axis. And then I've made up the table for vectors A, B, and C, which were provided. And then I've added a spot for vector E, which is the one that I am going to be calculating. If you want me to, I can show you how to add in vector C to calculate vector F in an additional video or in class. But I'm just going to do the two for this. So we are not going to be using vector C at all. So the first thing that I have done is I have graphed a line, and I'm trying to color code this. I'm not sure how well it's going to come across in the video. I've graphed vector A, so this is at about 15 degrees. And then I have graphed vector B, which is at 260 degrees. Now, the first thing we have to do here is turn these two vectors into triangles so that we can actually do our vector math from chapter 3. So vector A is pretty easy. To turn vector A into a triangle, which I am going to do here, I am just going to use this angle as our known angle, and then horizontal and vertical. So vector A would look like this. With this known angle of 15 degrees, this is 90, and the hypotenuse of our triangle is a magnitude of 30. Then we have vector B, which is right here. Now, vector B, the known angle, is the angle from the vector all the way around to the positive x-axis. That is not going to work for a triangle. So instead, what I'm going to do is I'm going to use this angle as our known angle, because from the positive x-axis all the way around to this vertical negative y-axis is 270 degrees. Since that's 270 degrees, and we know that vector B is at angle 260 degrees, we know then that the gap here has to be 10 degrees, which is a much more able triangle for us to draw. So we're going to turn this vector into a triangle. So it's going to look about like this one, except it'll be taller and skinnier. And then this is the angle that I knew of 10 degrees. And the magnitude of the hypotenuse is going to be the 35 from the table. Now, before we do anything else, we need to talk about our unknown vector E. Vector E, we have to infer where it's going to be. Now, this is not going to be the case in any other problem. In fact, it's not really the case for you today, because you have already done the experimental portion of this, and you know what direction your vector E should be in. But you cannot use your experimental data in your theoretical calculations. So we have to pretend that we don't know the magnitude or actual angle of vector E. And ditto when we do F later. So I know that vector E goes off in, trying not to fall here. There we go. I know that vector E goes off into quadrant 2. But I don't know its actual magnitude or its actual direction. So I'm calling its magnitude E, and I'm calling its direction theta. Now, I need to pick a side here to use as my theta for my triangle. So I am going to choose to use this as my angle for my triangle. So as I get off the wall here, that would give me a triangle that looks like this, where this is my known angle, which I'm going to refer to as theta, which is going to be confusing later. You know what? Let's call this a different letter. Let's call this a backup letter that we sometimes use in place of theta when we have multiple angles. I'm going to call this phi. Now, a phi is a circle with a vertical line through it. So this is the character that I'm using for my angle for the rest of this. And I'm probably going to forget that and write the wrong thing from time to time, so bear with me. That's important because this angle is not the same as this angle. And the full angle is theta. So that's why I am using a different character here. Just like 10 is not the actual angle for angle B. Angle B is at 260, but 260 does not work for our triangles. So we're using 10 instead. So phi is my angle. I know this is going to be 90 degrees because of the horizontal and vertical lines. And then the hypotenuse I'm going to call E. Now I have 3 vector triangles, so I can determine my components, my x and y components, just like we did in Unit 3. So the vertical line is going to be the y component, so this will be vector a, y, and the horizontal will be vector a, x. Then this one would be by and bx. And then ey and ex. So we just use our triangle trig, or our functions, sine, cosine, tangent, and we're going to determine ay, ax, by, bx, ey, and ex. Or at least we're going to write out the equations for them. So ay has to be equal to, it is opposite, so it's going to be sine. So 30 sine of the known angle 15. And then ax is the same except cosine. So 30 cosine of 15. Then for angle B, or for triangle B, vector B, our opposite is actually going to be bx. So if I go by is adjacent, so it's going to be 35 cosine of the known 10, and bx is going to be 35 sine of 10. Which brings us to EY and EX. Now, EY is adjacent to the known angle phi, and the hypotenuse of this triangle is variable E. So the y component would be E times adjacent makes it cosine of angle phi. And then ditto, but with sine for x. So we have broken our triangles up. Now, there is one thing left that we have to do before we can move on from this. We have to assign direction. Okay, we haven't done this much yet in the actual class, so I want to explain how this works. Every vector, we've already said this, every vector has a positive or negative value, depending on what direction it's in. And then for these, the actual vector does not have a negative sign because we reported the angles instead. But we're losing those angles when we go to this. So we need to report a positive sign or a negative sign for each one of these so we know what direction the vector is going. So to do that, we just go back to our graph, okay, where we measure relative to the origin. So the origin is going to be our known angle in each. So this is the origin for triangle E. This was the origin for triangle B, and this was the origin for triangle A. So relative to the origin, vector A moves in the positive x direction. So this is positive, and the positive y direction. I can't reach that. Step up here. There we go. Vector B moves in the negative y direction, so it's going to be negative, and the negative x direction. So this is also negative. And vector E is positive y and negative x. Now you can also figure this out using a pattern that you should have learned in geometry, where this is quadrant 1, 2, 3, and 4. In an ordered pair, x, comma, y. Quadrant 1 is positive, comma, positive. Quadrant 2 is, wrote it wrong, negative, comma, positive. 3 is negative, negative. And 4 is going to be positive, negative. Because on this side of the y-axis, x is positive, but on this side, x is negative. And above the x-axis, y is positive, while below, y is negative. So you can also use this as a shortcut if you know what quadrant your vectors are in. So since vector A is in quadrant 1, both should be positive. They are. Since vector E, red one, E, fifth letter of the alphabet, is in quadrant 2, then x should be negative and y should be positive, which is what we see here. And vector B is in quadrant 3, so both values should be negative, which is what we see. So I'm going to erase this because I need the board space. So this is breaking up into components. Now, from here, we need to fill in what's called a force table. And I will draw that out in just a second. And actually, I'm going to pause this while I draw some of it so that this video doesn't get ridiculous. All right, I have added the table, which has a column for the x dimension and a column for the y dimension, and a row for each of our three vectors. And FT just stands for total force, which is something you don't really need to worry about. I just always put that force table. I just always put it on my tables. So we need to fill in this table with the x component of vector A here, the y component of vector A here. So just these 6 values, these 6 equations, just need to go into this table. So I'm going to pause this again and do that real quick. And then we should be ready to move on with the part that is somewhat confusing and where people tend to get lost. Okay, so now the table is filled in. Now we need to write what's called a sum of forces equation. This is the goal. From here, we can actually start to solve this. Everything up to this point is kind of prep work, which you'll actually get fairly accustomed to by the end of this unit. But this table is a tool which you do not have to use, but it makes writing these equations much easier. Now, this is a Greek letter sigma. We use it to represent sum of. So this is the sum of forces in the x dimension. To get that, we just add up these 3 equations. So, vector A is 30 cosine of 15 plus, and in this case it's minus because it's plus negative. 5 plus negative 3 is 5 minus 3, or 2. So we're just going to go minus 35 sine of 10 minus e sine of phi. Am I running off the edge? Not quite yet. Okay. Now, here's one thing that you have to keep straight on these. I will tell you this for these problems, and this is going to be true for both your E calculation and your F calculation. The sum of forces is equal to mass times acceleration. Sometimes, though, like in this problem, the acceleration is 0. So this equation is equal to 0. Okay? Which is how we actually turn this into an equation we can solve. Okay, now we do it again for the sum of forces in y. So this column is going to be 30 sine of 15 minus 35 cosine of 10 plus e cosine of phi, and this is also equal to 0. Now, we know these both have to be equal to 0 because this is the canceling vector. The target should be perfectly centered within the circle on your table, which means that all of your 3 or 4 vectors are canceling each other out, which means the net force or the net movement is 0. There's nothing happening at the target. That's why we can say that these are equal to 0. From here, this is mostly algebra. And so the first thing I'm going to do is I'm actually going to calculate AX, AY, BX, and BY to simplify this calculation down. Simplify these two equations. Sometimes you can do this, sometimes you cannot. For all of your calculations in this lab, you can do this. So I'm going to pause this again to do that, and I will be back in just a moment. Okay, so what I have done to go from these two equations to these two equations is I have solved this and gotten 29. Okay. This and gotten 7.8. This came out to 6.1, or rather negative 6.1. And this came out to negative 34. And if you wanted to go ahead and simplify it down more, you could go ahead and subtract these numbers to actually get just one number, which I'm actually going to go ahead and do real quick. So 29 minus 6.1 gives us 23. And then down here, 7.8 minus 34 gives us negative 26. So this is negative 26 plus e cosine phi, and 23 minus e sine phi are both equal to 0. So now we have a very, very simple case of two equations, two unknowns. We don't know phi, and we don't know e. So we are going to solve one of these two equations for e, plug it into the other equation, and that will allow us to calculate phi, which I'm going to have to actually move my laptop to show you this part. So the view is going to change. So if you want to be able to see all of this, I'm going to step off screen. You might want to screenshot or take a picture with your phone if you can, this, in case you want to be able to look back at this without losing your spot in the video. So I will step off, and I am going to pause this and rearrange, and I'm going to rewrite those two last equations one more time before we start. Okay, so I have rotated a little bit so we can see the rest of the board. And as I said before, when you come into class, all of this will still be up. So these two equations, I have rewritten them and I've color-coded them so that they are just one color now, since it's more important that we track where the stuff comes from than it is to track the individual actual vectors that we started with over here, which is why all of this was color-coded. So now the first equation, the x equation, is in red, and that is written the same way it was here. The second equation I have switched because it was negative 26 plus e cosine phi. I have flipped it, so now it's e cosine phi minus 26, which should make the math and the algebra a little easier to work with. But I haven't actually changed the equation any. It's the difference between writing a plus b and b plus a. It's the same thing. So we're going to solve equation y for the letter e. And I'm going to try and find a way where I can do this without actually being in the way of what I'm writing. This should work. Okay. So we need to get e by itself. So the first thing we're going to do is add 26 to the other side. So e cosine phi. Well, that's a terrible phi. I'm going to do that again. There we go. Equals 26, because we would add it. Then we divide by the cosine of phi, which will cancel this. So that's going to give us that e is equal to 26 divided by the cosine of angle phi. And then we take this right here and we plug it in for E in this equation. So now I'm going to rewrite this equation, but I'm going to sub this in instead of E. And I'm going to step off this stool before I do so I don't fall over. Ugh. So the equation Y would become 23 minus, I always hate when this is a minus sign. It's always annoying. 26 over the cosine of phi times the sine of phi is equal to 0. Okay, now I'm going to do some algebra here, and I want to introduce something to you first off. I'm going to explain this with a slightly different method. A times B over C equals E. Well, if this is true, then A over C times B is also E. And that's what I'm about to do. I'm going to move the cosine of phi from being under the 26 to under the sine of phi, which is just slightly changing my fractions, because since this is true, moving this over here will not change my math at all. It's going to let me do something that's actually kind of cool. So I'm going to erase this and rearrange this again. So now it's 23 minus 26 times the sine of phi over the cosine of phi is equal to 0. Now here's what this lets us do. You might remember when we first talked about trig, I told you that the sine of theta divided by the cosine of theta is equal to the tangent of theta. At this time, we cannot solve this equation because we still have two phis. We have to consolidate them. In order to do that, we have to use this. So this becomes, in our one last step, 23 minus 26 times, actually I don't need the parenthesis anymore, the tangent of phi equals 0. Then we just have to solve this for phi, and I'm going to switch to just using one color here for this, and I'm going to go to here. So to solve this for phi, we would start by subtracting 23 to the other side, then divide by 26. So 23 divided by 26 equals the tangent of phi. So that's still on screen. It's small, it's tiny, it's hard to see, but it is still on the screen. Okay. So I'm going to shift this over a little bit to try to make it easier. And then we take the inverse tangent of both sides. So tan negative 1 of 23 over 26 equals phi. So you plug this into your calculator, and it gives you phi. Then, now that you have phi, I'm going to switch to blue here. You can take this number that your calculator gives you and plug it back in to this equation to get E. So that's how you get E and phi. And most of the time, that's where the work stops. That's where I'm going to stop this video. It's a lot shorter than I was worried. It's only about a half an hour long because I paused it in a few spots. I'm going to stop here, and I will explain where to go from this point in class tomorrow. This is not your actual final answer, okay, because your angle is wrong. The angle that you've got is phi. It's not theta. So if we rotate back over here, theta goes from here all the way around to here. Phi, the angle that we just calculated, is only from the positive y-axis to our vector. So it's just this little piece here. So I want you to take a crack at how we actually determine theta from phi for this example. It's not always going to be the same thing. You have to look at your graph to figure it out. But that is the end of this video. I hope you all find it enlightening, and I hope it's not too terribly terrifying for you. This is the basis of any equilibrium problem. So we will come back to this method several times in this unit, which is one reason why I decided to make this a video, because I think it will be a very valuable resource for you. Usually we won't have to break up this many vectors. A lot of times there's a lot of zeros in this table. But I will make a separate video and we'll talk about equilibrium problems on Friday, I think. So that is it for this video. I hope you guys are having a wonderful night, and I will see you all in class tomorrow. Bye.